And welcome to Equilibrium. Today we're going to take a look at what happens when the rate of a forward change equals the rate of a reverse change. Oh, I've just given you the definition of equilibrium. Go me! All right, so let's see. Types of equilibrium. Depends on exactly what situation you're dealing with. If you're dealing with chemical reactions, then you have what's called reaction equilibrium, where the rate of synthesis is equal to the rate of decomposition, as an example. So nitrogen and oxygen are forming nitrous oxide at exactly the nitrogen monoxide at exactly the same speed that NO is breaking back up into N2 plus O2. It's kind of like, imagine you're building something out of Legos and you get to a certain point and what you're building begins to fall apart. So if you're putting Legos on your construction at the same rate Legos are falling off your construction, that's equilibrium. Or if you're putting them on at the same rate someone else is taking them off. Phase equilibrium is when there's an equilibrium between phases. For example, if water boils, it begins to condense. And eventually, if you keep this in a closed system, the rate of boiling and the rate of condensing will equal each other. For every molecule of liquid that turns into a gas, another molecule of gas turns back into a liquid. That's phase equilibrium. Third, we have solution equilibrium. This happens in solutions. So silver chloride dissolving in water, which it does very poorly. Silver chloride, when every formula unit of silver chloride dissolves, for every ion of silver or chloride that comes back to reform the solution of the salt. Wow, I am really messing that up. Let me try that again, shall we? For every AgCl that dissolves, one AgCl will precipitate. And that is going to take place when the solution is saturated. If you have an unsaturated solution, the rate of dissolving is faster than the rate of precipitating. But if you're at equilibrium, you have equal rates between dissolving and precipitating. There, got it. I was distracted. It's been raining all morning, and I happened to look out, and it looks like the sun might be starting to come out. Woohoo! I am really happy about that. Okay, anyway, nothing to do with what we're doing here. Properties of systems at equilibrium. First, the definition of equilibrium, the rate of the forward change equals the rate of the reverse change. That's just what equilibrium is. And as we took a look at in the last topic, since both forward and reverse changes are happening at the same time, they're both spontaneous, delta G is 0. And equilibrium can only be maintained in a closed system. As long as you don't allow any factors that affect reaction rate to change, then equilibrium can be maintained indefinitely, but only in a closed system. And by the way, we call this kind of equilibrium dynamic equilibrium because it's not just sitting there, it's constantly in motion. When you're just standing on a treadmill and neither is moving, you're not at equilibrium. Equilibrium is only achieved when there's movement, and that's why it's called dynamic equilibrium. Different reactions will reach equilibrium at different concentrations of reactants and products. The concentrations are not equal. They're constant, they're not changing, but they're not equal. The rates are equal, the concentrations are constant. And what those concentrations are will give us a clue as to how far a reaction went before reaching equilibrium. The ratio of products to reactants at equilibrium is called the equilibrium constant. But this only applies for reactants and products that are gaseous or dissolved in water. Solids cannot be involved in this. Okay, so how do we set this up? How do we figure out what this proportion is? Well, we use this mass action expression for our equilibrium constant, KEQ. So let's say we have this system at equilibrium. A and 3B form 2C at the same rate that 2C breaks back down into A plus 3B. So first we're going to put the products on top and the reactants on the bottom. And of course, the products is the stuff on the right side. So this will go on the top of our proportion. This will go on the bottom of our proportion. Numerator, denominator. We're going to put these into brackets to represent molar concentration. So what is the concentration in moles of substance per liter? And we can use this for solutions or we could use this for gases. So we're going to place C on top because it's a product. We're going to put A and B on the bottom because they're reactants. But wait, there's more. The plus sign becomes a times sign. And coefficients become exponents. So 3b becomes b cubed, and 2c becomes c squared. That is a mass action expression. It represents the proportion of products to reactants. We can now plug in numbers based on experimental data to calculate our equilibrium constant. So let's suppose at equilibrium, these are the concentrations we find for these various substances. All we need to do is substitute into the mass action expression. A is, we're going to do C first, huh? Okay, so C is 4.0 molar, so we make that 4.0 molar squared. A is 2.0, so we'll pop the 2.0 in there. B is 6.0. So literally now all we have to do is take 4 squared, divide it by 2 times 6 cubed. And when we do, we'll get a number. Now, what exactly does that number mean? The smaller the number, the faster equilibrium was reached because we had very little in the way of products and more reactants. Don't know what I'm talking about? Well then, let's have a look at it. KEQ tells us various things. If KEQ is less than 1, remember KEQ is products over reactants. Therefore, any value smaller than 1 means the denominator will be larger. We'll have more reactants than products. That means the reaction didn't go very far. We still have most of our reactants made. If this was pancake batter turning into pancakes, we'd still have mostly pancake batter and very few pancakes. If KEQ is greater than 1, then that means we used up most of our reactants to make the products. There'll be more products than reactants, and because products is in the numerator, if the numerator is bigger, the value will be, the proportion will be greater than 1. This means we used up most of our pancake batter and we have mostly pancakes. If KEQ equals 1, that means the numerator and denominator are equal. Yahoo! Gesundheit. This almost never happens. Usually your KEQ is either going to be greater than 1 or less than 1, and usually by quite a large amount. Finally, if KEQ equals 0, that means the numerator is 0. And since the numerator is products, that means that there are no products. It's like we have pancake batter, but we never made any pancakes. And if KEQ equals infinity, that means that we used up all of our pancake batter and all we have left is pancakes. The reaction goes to completion. So if KEQ equals 0, that means the reaction never started. And if KEQ equals infinity or undefined, then that means our reaction went to completion. So we can actually compare KEQ values. Solution equilibrium works very similar. Since equilibrium constants are used for aqueous or gases only, we can't use KEQ to determine how soluble something is before it reaches a saturated solution. So what we use is what's called a solubility product constant. For soluble solutes, all of the solute will dissolve. Therefore, KEQ will be infinity. We can't even use KEQ for this purpose anyway. So, for example, if, let's say, we dissolve something in water, let's plop that in there, Silver chloride is listed as being insoluble on reference table F. That doesn't mean it won't dissolve. It only means that a tiny amount of it will dissolve before making a saturated solution, before reaching equilibrium. So let's get in on this thing. Let's zoom in and have a look at what's going on. You'll notice that the ions begin to dissolve. But very quickly, we reach a saturated status, and no more can dissolve until some precipitates. And you'll notice here comes precipitating, and more dissolves. Some is precipitating, more dissolves. Some is you see that? The rate of precipitating equals the rate of dissolving. And what we're going to look at is what is the concentration of our dissolved ions when the solution is saturated. And that will give us a value called our solubility product constant, also known as KSP. So here's how that works. KSP is equal to the concentration of the positive ions to the power of whatever the coefficient is, times the concentration of the negative ion to the power of whatever its coefficient is. So, for example, let's say I dissolve silver bromide into silver ions and bromide ions. The KSP will be equal to the concentration of silver ions times the concentration of bromide ions. Let's say we dissolve lithium carbonate. Well, it's going to break up into lithium ions and carbonate ions. However, we need to balance, so we put a 2 in front of Li plus 1. So when we do the KSP, it will be equal to the concentration of lithium ions times carbonate ions, but we have to take that coefficient in front of lithium and turn it into Li plus 1 squared. Now, we can actually compare KEQ values for these different substances. Silver bromide, when you multiply the ion concentrations together, you get 10 to the negative 13th. That's a very small number. For lithium carbonate, when you multiply across, you're going to have 10 to the negative second. And what that tells us is we're multiplying bigger numbers to get a bigger answer. That meant that when you made a saturated solution, lithium carbonate had a higher concentration, meaning lithium carbonate is far more soluble than silver bromide is. Silver iodide would be the least soluble thing on this entire table. Lithium carbonate would be the most soluble thing on this table. So we can use KSP values to predict which substances are going to be more soluble in water. And that's as far as we're going to take it. If you take a college level course, you'll actually calculate KSP and use KSP to determine what the molar concentration of a saturated solution is. But we're not going to get into that at this level. We're only going to have one more topic left to go, which is how to make equilibrium do what you want it to do. So until we do that, have a wonderful day, week, month, etc., and so forth. Be good. Take care. Bye.